Hello, my name is Pedro Conde and I'm presenting the work called Adaptive TTA Accuracy Consistent Weighted Test Time Augmentation Method for the Uncertainty Calibration of Deep Learning Classifiers, authored by myself and Cristiano Prombida, both from the Institute of Systems and Robotics, University of Coimbra. Deep learning-based image classifiers are now present in numerous real-world applications. For this reason, we need to know not only how accurate, but also how reliable they are. How much do their confidence values differ from the true likelihood of correctness? This leads us to the problem of uncertainty calibration, also called confidence calibration or simply calibration. To tackle this type of problems, we propose a novel technique based on test time augmentation called adaptive TTA that leverages an adaptive weighting system to improve uncertainty calibration without affecting the model's accuracy. But first, we will look closer into the problem of uncertainty calibration. If we consider an input space, the corresponding set of true labels, and a model whose output is a probability vector, in our case a deep neural network, we say that the model is calibrated if, in each prediction, the largest confidence value on the left side of the equation equals the true likelihood of correctness on the right side of the equation. For example, for the sake of intuition, a calibrated model would correctly classify, in the long run, 70% of the predictions with a confidence value of 0.7 associated. Of course, perfect calibration is impossible to attain in practical scenarios. Furthermore, the true likelihood of correctness, on the right side of the equation, cannot be computed using a finite number of samples. This motivates the need for evaluation metrics to evaluate uncertainty calibration. Before going into evaluation metrics, it's important to emphasize the relevance of this problem in modern deep neural networks. In fact, it has been shown that modern neural networks are tendentially less calibrated than older counterparts, even when their accuracy is higher. A popular evaluation metric for uncertainty calibration is the Brier score, a proper scoring rule that computes the squared error between the predicted confidence value and its true response. Another popular calibration metric is, for example, the expected calibration error. We will use the expected calibration error in the optimization process of our method, but not for evaluation, given some pathologies of this metric that have been identified in relevant literature. We now want to understand how we can approach test time augmentation in the context of uncertainty calibration. In fact, a classical approach to test time augmentation, even if optimized to address uncertainty calibration, can corrupt the accuracy of the model. For this reason, we developed adaptive TTA, that by leveraging an adaptive weighting system can be optimized to improve uncertainty calibration without the concern of affecting the accuracy of the model. We will now describe adaptive TTA. Let us first start by noticing that, since some types of transformations have random parameters, these can be applied multiple times in the same augmentation policy. In equation 3, the vector Pij represents the instance j of an augmentation of type I, while the vector P0 represents the output of the model with the original input without transformations. In our method, we assign a weight for each augmentation type and also define the weight omega star that will work as an upper bound for the adaptive weight omega bar. This adaptive weight, in the way that is defined in equation 4, will allow us to optimize the transformation parameters and the upper bound using a validation set, so that we minimize uncertainty calibration but never alter the accuracy. In our case, we make this optimization using the expected calibration error as a loss function and an Elder-Mead optimization algorithm. In our experiments, besides adaptive TTA and the vanilla approach, which is always a ResNet type deep neural network, we will also use temperature scaling. Temperature scaling is a popular and widely used post-hoc calibration technique and a common baseline for this type of experiments. In this technique, we optimize a parameter t using a validation set that will scale the softmax function in order to obtain better calibrated predictions. Just like adaptive TTA, temperature scaling does not alter the accuracy of the model. In the experiments, we apply adaptive TTA with 7 different augmentation policies. The first 4 only use one type of augmentation. Adaptive TTA flip consists of a single flip around the vertical axis. Adaptive TTA crop consists of 5 random crops of fixed rate. With adaptive TTA brightness, we have 5 random brightness changes within a given interval. And with adaptive TTA contrast, we have 5 random contrast changes within a given interval. The remaining 3 augmentation policies have multiple types of augmentations. Mix 1 combines flip and crop augmentations. Mix 2 combines the augmentations present in Mix 1 with also brightness augmentations. Finally, Mix 3 combines all flip, crop, brightness and contrast augmentations. We'll now present our results in the datasets CIFAR10, CIFAR100 and aerial image dataset. Given the randomness inherent to some transformation parameters, we will present some results in the form of box plots resulting from 10 different experiments. On CIFAR10, the only single transformation approach that outperforms temperature scaling is adaptive TTA flip, with the mixed approaches accomplishing the best results in this case. On the CIFAR 100 dataset, no single transformation approach was able to outperform temperature scaling. Nonetheless, the mixed approaches present good results. Specifically, Mix 1 and Mix 2 are able to obtain better calibrated outputs than temperature scaling. Finally, on the aerial image dataset, we find an interesting phenomenon. In this case, temperature scaling actually worsens the calibration of the model. Interestingly, adaptive TTA can still accomplish good results with both adaptive TTA crop and all the mixed approaches. We conclude that adaptive TTA can outperform temperature scaling on all the 3 datasets used in the experiments. Even on the aerial image dataset, where temperature scaling is not capable of improving uncertainty calibration, we find that it is possible to accomplish good results with adaptive TTA. Of the evaluated approaches, we find that, in general, it is a good idea to use different types of augmentations, since the mixed approaches seem to be the more consistent in terms of results. Additionally, we can conclude from the results that the flip and crop transformations are generally present in the best performing approaches to adaptive TTA, while the contrast transformation presents some evidence that can produce unwanted effects on uncertainty calibration. Thank you for watching this presentation.